Okay, so from what you guys gave me, I have this table filled out. These are showing our alleles, and we have diploid chromosomes, which means they are shaped like this guy, and there are two halves. We can separate them into two locusts. This is one locus, this is the other, and anything that reproduces sexually is diploid, because remember in mitosis, which is where cells split and reproduce, they pull their diploids apart and then they make this allele and this allele individual. So they separate the original diploid chromosome. So if these are all diploids, each letter represents its own allele. So this is two alleles, two alleles, two alleles, two alleles. Where I've only put one, those are indeterminate so far. So, Dad doesn't really text, so I don't have his data yet, but it's really the key to all of this. It's funny. What we can see right here is that Mom brought in with her a recessive trait for having hitchhiker's thumb, where it bends back. And because she brought in that recessive trait and Dad also brought in that recessive trait, we can assume, which means we can test that hypothesis right here by seeing if he has hitchhiker's thumb. So if that's true, he does have hitchhiker's thumb, this math checks out. That Punnett square would say that recessive, recessive, and recessive, 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 recessive and recessive, recessive on both sides equals 4 blocks of recessive. So Mom and Dad got married, had babies, and they had hitchhiker thumbs. Because they both had the recessive gene for hitchhiker thumb, all of us got hitchhiker thumb. We didn't have a choice. There's no way we could have had a 90-degree thumb angle. We all got hitchhiker's thumb. Next is the hair on the thumb. Again, he hasn't responded, but Mom doesn't. I don't. Amber and Taylor do. What I can assume there is that he does, and he has it recessive. Because if he had it dominant, I wouldn't have a recessive up front. So we can do that math. So Dad brought in dominant D, Mom brought in recessive. So what we can see there is that, that's supposed to be a little d, that's supposed to be a big D. So what we can see there is that somebody got it double dominant, thanks to Dad, and then somebody could have got dominant recessive, recessive, recessive. So this is me right here. There was a 25% chance that could happen. And then Amber and Taylor, there's a 25% chance you could have gotten it dominant. That's this right here. And then you would have a more likely chance to pass that hair on the middle digit onto your children. But there's a greater chance, this 50% chance, that you got that recessive. So what I can assume there, because he has a recessive and Mom has a recessive, that you two both got recessives. And the way that we can test that is to see if your spouse has hair on their digits and then test that on your children, or we could go up to grandparents and see what they have. Next is the tongue. That's the really interesting one, because that is a genetic mutation in humans that happened about 100 years ago. And we don't really know why, who, what, when, where, or how. It doesn't help us in survivability, so it's not in the realm of natural selection. But it's just interesting to study, and it helps us see how Mendelian genetics do transition over to human populations. Mendelian genetics is like the peas, a purple pea and a white pea come together, and then their baby has pink flowers instead of purple or white because they are co-dominant. Next is tongue. Okay, so Dad can't do it. We can all make fun of him because we all can. Mom can do it. What's really, really interesting about this one in particular, all three of us can roll our tongues. Mom can roll her tongue, but Dad can't, which means that Mom brought in a dominant gene for tongue rolling, which only developed 100 years ago. So that can tell me that we can do this math. We can go, Dad brought in, well, we'll do Mom first because she's got dominant, 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 recessive, 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 recessive. Those little teaser dads. Okay, so boom, right off the bat, Mom says, bringing in my dominant genes. Boom, 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 boom. All four, there's a 100% chance that we would inherit her dominant T up front, this guy, and then either a recessive or a dominant. Doesn't really matter because this dominant trait will kill out the recessive over a few more generations in our family. We will lose that genetic variation of not being able to roll our tongue because Mom's gene for rolling your tongue is more powerful than Dad's gene for not rolling your tongue. So it gets preferred genetically because it's a stronger gene. When the cell pulls it apart, it's more likely to stay together. It's more likely to stay together. Dad's recessive is more likely to get damaged or fall apart with this bigger, stronger gene right here for that tongue rolling existing in the same diploid chromosome. So that's our, it's called your character stats for a population. Typically there are like over 300 of these for a small population of, say, frogs living in a pond. They'll have over 300 genetic variation traits. As a family, we have more than 3, but you need at least 3 to calculate genetic variation, which is what I'm about to do next.